Yeah, so you've probably done this in statics course, where you draw a free body diagram, and from the free body diagram you figure out unknown forces, right? Jacobian is a way to do that without drawing free body diagrams, so it's a nice thing, right? You wish you knew this when you were doing statics. So just going to put a body, pin it to the ground, apply some forces. Yeah, so if there's a body and forces applied, let's say in the absence of the torque, okay, if there are forces applied and if those forces don't pass through the pin joint, then this thing will start turning in crazy ways, right? Your goal here is to compute a torque such that this object is in static equilibrium. So given F's, compute tau 1 to keep the object in static equilibrium. Yeah, so what we do here is we use what is known as a principle of virtual work. You might have heard of this in maybe in the statics class, or maybe they don't get to this. What you do here is you assume that because of forces F, the object is displaced by, or the center of mass is displaced by a distance dr. So virtual work is force times dr. So here dr is the virtual displacement. It's not real, it's fictitious. Okay, something about dimensions. F is 1 cross 2. So any force in plane has two components to it: a force in the x direction, force in the y direction. Dr is 2 cross 1 because there'll be displacement in the x and y direction. So when you take the product F transpose times dr, work will be a scalar. This will be 1 cross 1. Yes, similarly, if you apply an external force or external torque, tau, then that tau will cause a virtual rotation, okay, not real. That would be torque tau t theta. Now this thing is 1 cross 1 because this object is in 2 dimensions, so it can only rotate in one way, and this is 1 cross 1. What is Jacobian? This is 1 cross 1. Now what we do is we equate these two things. Because the work done by those forces F should equal the work done due to tau. Just a minute, I'm almost done with the derivation. Okay, so let's equate the two. I can divide both sides by d theta. Okay, but this quantity here is the rate of change of, think of it in terms of the position of a point, which is F, with respect to the independent variables theta or q. So this is basically the Jacobian. And so we have tau transpose is F transpose Jacobian taking transpose of both sides. So transpose of transpose is that quantity itself. And then when you take the transpose of this thing on the right side, this is one of the identities given in homework 1. You have AB transpose is P transpose A transpose. So it'll be J transpose F transpose of transpose. This is from AB transpose is P transpose A transpose. So to finish up, tau is J transpose F. So this is theta 1. This angle here is theta 2. Okay, and there is clearly gravity. Now, under gravity, this system with, let's say, one center of mass here, another one here, just cannot stay in equilibrium in that configuration, because gravity will pull it down, will make those links straight. So what you need to do is you need to support the pendulum with a torque. Let's call that torque T1 at joint 1 and torque T2 or tau 2, sorry, at joint 2. And you know that the effect of gravity is to pull this down with a force of m1g and this one with a force of m2g. So here the question is compute tau 1 and tau 2 such that the pendulum is in static equilibrium. So theta 1 and theta 2 are not equal to 0. It's some angle. Okay, so in a problem you could specify theta 1, theta 2, and you can basically do it for a numeric value, but we'll just do it sort of symbolically where we are trying to derive a general formula. Now this calculation can be done using things you've learned in statics. What you'll do is you'll draw a free body diagram, right? You'll separate out each pendulum. You will draw all the forces. There'll be forces at the pin joint, and then you can solve for the forces and eventually solve for the torques. Or you could also do moment equilibrium about this point. Let's call that O. It's also O0, O1, O2. This is, I'm just naming them so because if you recollect, I had put frames along these x1, y1, x2, y2, then right here there's another one. Let's just take this frame x0. Yes, you could take moments about O1 or O, and that will help you to solve for tau 1, and you can take moments at O2, and then that will help you to solve for tau 2. What I'm going to show you is that you can do this without drawing a free body diagram, just using the Jacobian. So the derivation showed us that you could essentially use this formula to solve for the torque. So how will this go? Well, there are, in this case, there are two forces. So I'll write it as tau 1, tau 2 as the torques at the two joints. This is actually, in this case, it's the sum of the forces because there's not one but two forces. So the first force is due to m1g. So now when you write this forces, this is written in the global frame x0, y0. So there's only a force acting in the vertically downward direction. So I actually did an error here. This should be 0 and minus m1g. So why did I write that? This is essentially the force at g1 in frame 0. There's been x component and a y component, but the x component is, which is in this direction, is 0, and the y component is m1g. Okay, and then I need to figure out what the Jacobian of that particular point is. So Jacobian of g1 plus Jacobian of g2, 0, same thing, m2g. Okay, what remains now is to compute these jg1 and jg2. So normally you would compute them, but here I'm in luck because in my last class I actually computed Jacobian of jg1 and jg2. So I'm just going to go back and show that to you and then flash back to this. So this was a problem. We've tried to compute jg1 and jg2. The answer came out to be here maybe. So this was jg1. Just going to write that down. And then I told you you need to solve this yourself at home. This is essentially jg2. Okay, so I'm just going to copy this there. Just because I've done it before. So let's copy that. So let's this was computed earlier. So we just substitute that. Tau 1, tau 2 equals, I'm going to write jg1, that is c1 cosine theta 1. Okay, so by the way, this is, so this is jg1. But remember, I need to take the transpose of this. So the first row, first column will become the first row. So I do that directly. I will not really write another step. So C1 sine of theta 1, that would be the transpose 0, 0. Write it down like that. Yeah, I did a mistake here. This should be transpose, right? There's a transpose here. So this is JG1 transpose 0 minus M1G plus, I'm just going to continue on the next line. C2 cosine theta 1 plus theta 2 plus L cosine theta 1 C2 sine theta 1 plus theta 2 plus L sine theta 1 C2 cosine theta 1 plus theta 2, then C2 sine theta 1 plus theta 2, and then the usual 0 minus M2G, where this quantity here is JG2 transpose. Then remember that this is a 2 by 2 matrix. Similarly, this is a 2 by 2 matrix. Okay, so you can do the math on this. I'll just write down the formula, final formula. So simplifying, multiplying, and simplifying will give you tau1, tau2 as. So remember that when you take the multiplication of the first part, will be this whole thing will be 2 cross 2 times 2 cross 1. So that will be 2 cross 1. Similarly, this will be 2 cross 1. So what you end up with is 2 cross 1 plus 2 cross 1 is 2 cross 1. So the answer would be minus m1g c1 sine theta 1 minus m2g c2 sine theta 1 plus theta 2 minus m2g l sine theta 1, and then second row m2g c2 sine theta 1 plus theta 2. Okay, that would be the answer. Okay, so you could potentially check this answer by trigonometry, by doing static equilibrium, Freeburg diagrams.